So, second question, and I looked at the first two questions before I started today, and the other, I think, four or five questions are a complete mystery. So, we'll see what we get when we get there. Yeah. Anyway, for now, Rick, who we know, asks, "Mind if I take it back to basics?" Sure, of course. I believe I know the answer, but others may not, and so yeah, why not? Why not? Come on, let's do this. So we should all be washing our hands. Yes, that's true. Not just for general hygiene, but to prevent contracting SARS-CoV-2. Yes, also true. And if we can't destroy this thing with a vaccine or an antibiotic, yeah, okay, I get where this is coming from. How is soap effective? Yeah, fine. Good question. Does it have to be basic, antibacterial, whatever, that lava soap? Oh, nope. Yeah, yeah, the answer is nope, it doesn't. Yeah, they all work. Okay, so to understand why soap works, you got to know your enemy. So you got to look at a coronavirus, and so here's our virtual coronavirus right here. So on the inside, you've got a couple of things. You've got the genome, which is just a long string of RNA. It's very fragile, but it has a really good set of bodyguards. And those bodyguards are called the N protein. It stands for nucleoprotein. And N works like a little spool. You wrap the RNA around it, we think, and you just have thousands and thousands of N's all along this long coily piece of RNA. And that's what's going on the inside. Then this is the rest of the virion, the rest of that virus particle, the sort of ball with spikes on it. That is all the delivery mechanism. So the RNA can work, but only if it arrives intact inside of a cell, and that's what the rest of the virion is for. It is the delivery vehicle. So nucleoprotein has to be on there to protect the RNA, or else the RNA just falls apart. Yeah. One thing soap does, it's going to pull nucleoprotein and RNA apart, and so RNA is going to be very fragile, and it's just going to shatter into little pieces fairly quickly, yeah. So that's one way. Second thing, outside of that nucleoprotein, you've got a membrane. So here's our bigger sphere. We had a little sphere inside. Yeah, just like that model of the planet where you get the core and the mantle and whatever. Only instead of a mantle, we're going to have a protein called M, and it doesn't stand for mantle protein. It stands for membrane protein, which is kind of a dumb name for it. But yeah, people used to call it the matrix protein, and I kind of like that because it's a cooler sounding word. But M's job is to collect everything together in order to make this little coronavirus particle. And so M will grab onto the nucleoprotein, the N protein, and M might even grab onto the RNA itself, and M will also grab onto the other proteins that you need to bring together, boop, this little thing, which is the delivery vehicle. M is super sensitive to soap, and if you mess up M, it's called denaturing a protein. It's like what happens when you cook an egg. Then M cannot function. And M's job is first to build the particle, put it all together, and then second, we think the M is also involved in opening up the particle, getting it ready to enter the cell. So M is attached to all these things on the inside of the virion, and M has to let go. And it does this once the virus has already got inside of the cell. We think there are a couple of signals that make it do this. And the other protein you need is the spike protein. Spike's fairly tough in this case. It's going to be the one that sticks out of the coronavirus, those little things on the top. And spike protein would also be sensitive to a fair amount, like a lot of soap. But the other component I haven't mentioned doesn't actually come from the virus. This is a membrane. It's like a lipid bilayer, just like the membrane on the outside of the cell it just came from. Coronaviruses are like one of those serial killers you hear about in the movies and occasionally in real life that wear their victim's face over their own face. You know, like that? Yeah, exactly like that. Coronaviruses steal a bit of the, it's actually the Golgi apparatus membrane of the cell, and they just take that from the cell and they put all their proteins in it, and they're going to rip it off and carry it outside the cell. It's fairly gruesome, actually. And this entire bubble has to remain intact, or else the whole virion just falls apart. And so, let's see, we've got soap can hit the nucleoprotein to make the RNA shatter. It can hit the M protein to make it so the nucleoprotein never gets out. It can never see the light of day. It can hit the spike protein to unfold it so that the virus can't get into the cell. And it can also pop the actual membrane around the virus. And when you pop that, then none of the pieces that you need to get this thing into the cell work anymore. Because on the way into the cell, the virus is subject to a lot of really strong enzymes and acidic pH. And these things together will break down that genome, and it won't make it. It won't make the journey. So yeah, with SOAP, you're attacking the delivery vehicle in the hope that it's not going to work anymore, and it is super effective. Probably popping the membrane is the number one mechanism. Probably scrambling the M is the number two mechanism. Once the membrane is popped, then popping the N protein off the RNA is probably the third mechanism. And I would say disrupting the spike might be the fourth mechanism. I'm just eyeballing this based on which things hold together a little bit better when you solve their protein structures. Yeah, somebody could actually do this test if they could purify all those things, which is a monumental task. But leave that to somebody else for right now. So there you go. That's far more of an answer than you probably ever wanted or needed, but you got it. And what you do with it is totally your business. Have a good day. This is Ask Dr. Ben.